So suppose we have a function, basically we want to evaluate this integral, bx times f of x, and f of x is even. B has this property which is basically saying that b is not an odd function. If this were -1, then this would be an odd function. So b is not an odd function, but satisfies this property. So we're sort of hinting that the name with b is likely to have a branch cut. Anyway, if b times f is well behaved at infinity, so that when we do the circular contour radius r going out to infinity, then that tends to 0. And there's also no poles on the real axis, so b times f doesn't have any poles on the real axis. Then it turns out we can derive this formula where we're summing the residues just above the axis. Now, this is a formula which you should not try to remember. You should, or at least be aware that there could be a formula, but this is something you should definitely not try to remember and quote. You should always just derive this from first principles each time. The thing that you do need to remember is the contour you need to use for this type of problem. So if we do have a branch cut, this actually works whether, even if there's not a branch cut and this property is satisfied, this still works. But assuming that there is a branch cut along the real axis, then the crucial thing to remember here, which is saving you time, is that we're going to be able to use this type of semicircular contour. So it's meant to be a semicircle to derive this. So I'll derive this general case and then do an example at another time. So we can use this semicircular contour and consider limit as r goes to infinity, epsilon goes to 0. So as usual, this distance here is epsilon, this semicircle is radius r. So limit as r goes to infinity, epsilon goes to 0 of bz fz. So we're just doing this general case. So the integral we want to evaluate is I, and we can see as epsilon goes to 0, r goes to infinity. That's the integral we want here. Then integrating around here, I'll skip that step because basically what we're assuming is that this is going to 0 fast enough as x goes to infinity, or as this goes to 0 fast enough as z goes to infinity. So I'll just skip that bit around there, assume it goes to 0. Then the important bit is this bit here. So what do we have here? So here we've got z equals r times e to the I pi. I'll write it like that. Okay. And r is ranging from infinity down to 0. Which means that if I do dz, then that's equal to minus dr, because e to the I pi is -1. So this integral along here is the integral from r equals infinity to 0 of, and we've got b of r times e to the I pi times f of minus r, and we've got dz is minus dr, so we've got lots of minus signs here to take account of. Right, so we've said that f of minus r is the same as f of r. That's what even means. So this becomes f of r. I've also got possibly limit as epsilon goes to 0 of this bit around here. So from pi, theta equals pi to pi by 2 of, b of z and f of z, where z is little circle around here. Again, I'm going to assume this goes to 0. Which it will do if things are nicely behaved. This is really why you shouldn't try to remember this formula, because you really need to derive it in each case and check that this really does go to 0, and check that this bit around here really does go to 0. But the important thing is really what happens here. So I'll just make some space here. And we can rewrite this now as I. Okay, well, I'll put 1. Now, think what happens here. We've got a minus sign here, infinity and 0. So I use swapping the integral limits to get a plus sign here. And this is the same as f. And I've said that b of minus x is just alpha times that. So in the end, I've got 1 plus alpha. This is actually just equal to alpha times the integral. So basically that's all I need now, because to show this result, because this, as always, by the residue theorem, is just 2 pi I times the sum of the residues inside the contour, which are basically, as R goes to infinity, any residues of poles which are above the real axis.